So now we're going to start talking about something that is very important, units. And I think this is a good illustration of the importance of units. 1999, NASA lost the Mars Climate Orbiter. It crashed into the surface of Mars. It was supposed to orbit Mars and collect all kinds of useful information. $125 million project. It's gone. It got too close to the surface. Its orbit wasn't correct, and it crashed.
Do you not have the slides on campus anymore?
Yes, they are on campus. So, of course, there was an investigation into this. Turns out what had happened, there are lots of people working on a big project like this. So the Mars orbiter gets up there, and they realize, okay, this orbit is not quite right. We need to make some adjustments. So there's software on the orbiter, and it's using one set of units, and there's engineers and scientists down here on the Earth calculating the new trajectory that it needs, and they're using a different set of units. They got calculated in inches and stuck into the computer. The computer was expecting centimeters. Dumb, right? Units are really, really important. The root cause of the loss of the spacecraft, a failed translation of English units into metric units. We do not want to be like those people, right? So in chemistry, units are also critical. Without a unit, a number doesn't mean very much. If you go to McDonald's and they say, well, I'd like to take your order, what would you like? And you say, I want 5. What are you going to get? A puzzled look from the worker, right? 5? 5 what? Number 5? You want fries with that? They don't know what you want. The unit is really important. There are 2 major unit systems. The metric system, which most of the world uses, and the English system, which we continue to hold on to here in the United States. The system that scientists use is the International System of Units. It is based on the metric system. There are some very subtle differences between the metric system and the SI system. I don't consider those differences to be important at all. And so as I talk about it, I will use metric system or SI system interchangeably. Really the only difference is what the base unit is. And that's just not that important if you ask me. These are the base units in the SI system. So there's units for length, mass, time, temperature, and amount of substance. Those are ones that we'll run into in chemistry. There's also a unit for electric current and for luminous intensity, and that's there just for completeness, but we're not going to use those at all. So kilogram, meter, second, Kelvin, and mole, and their abbreviations. So for length, the base unit is a meter, and the abbreviation is a lowercase m. There are places where spelling, punctuation, capitalization, those sorts of things are very, very important, right? If you put in your password and it's case sensitive and you have a lowercase a instead of a capital A, is it going to work? No. If you're sending an email to your boss explaining why you're going to miss an important meeting and you get one letter wrong, is your boss going to get the email? No, because that's a situation where details matter. And so there are places in chemistry where details matter, and I'm just not being a hard head about this, it's just how life is. Sometimes details matter. So the abbreviations are important because that letter M gets used for a lot of things. So the abbreviation for meter is a lowercase m. It's very helpful to have an idea of how large these units are. Now, there's a picture there, but here's an actual meter stick. So a meter stick is a meter long. And if we look at the English side of this, it's 39 point something, 39.37 inches. So a yard and a meter, roughly the same size. And having a clue about that, then if you do a calculation and you come up with a human being 7 meters tall, is that even possible? Could a human be 7 yards tall? That'd be 21 feet. No, that's not going to work, right? So when we have an idea of how big the unit is, then we can have an idea of whether our answers are ridiculous or not. For mass, the SI unit is kilogram. A kilogram is roughly 2 pounds. So if you weigh 100 pounds, then you're going to weigh about 50 kilograms. So that makes you sound thinner, right? Mass and weight are not exactly the same thing, although we tend to use them interchangeably. If you are in the same gravitational field, you can use them interchangeably, no problem. But weight is actually gravitational pull on an object, it's a unit of force. Whereas mass is a quantity of matter. So if you weigh 130 pounds on Earth and you go to the moon and you stand on a scale, because the moon is smaller, its gravitational pull is less, the scale's going to say that you weigh 21.5 pounds. Are you smaller in size just because you went to the moon? No. That's just gravitational pull. Your mass is exactly the same. You still have the same number of atoms and molecules. So your mass is the same on every planet. So as long as we all stay on Earth this semester, then we can just use those terms interchangeably. Nobody's planning to leave the planet, are they? I don't think so. Kilogram is kind of a large unit for use in chemistry. 2 pounds, we don't often do experiments where we're using 2 pounds of stuff. So we more typically use the gram. A gram is 1/1000th of a kilogram. I think it's easier to think of it this way. We're going to learn about the metric system in a couple minutes. A kilogram is 1,000 grams. We have all of these different units because it's helpful to have a unit that is roughly the same size as the object that you're measuring. So I live in Reedley and I drive to Fresno every day, and it's roughly 30 miles. I choose mile when I express that distance because I'm going to have a reasonable number, right? 30 miles. If I express that in inches, it'd be this huge, huge number, right? And so we don't use a unit that's much smaller or much larger than what we're weighing or measuring. So we do this in the English system. You know, a piece of paper, a notebook paper, you're going to measure in inches, you're not going to measure in miles, right? So we need all these different units so that we can have appropriate sizes. To get an idea of how much a gram is, a nickel, which is 5 cents, weighs about 5 grams. So 5 grams, about the mass of a nickel. It's a small amount, right? The second is the same as the second we use in everyday life. Thank goodness. How these units are defined, they are all defined in a very, very precise way, and that's all explained in your book, and you should read that, but I'm not going to test you on it. The second was originally defined in terms of a day and a year. You know, okay, a year is 365 and a quarter days, and then you take the day and divide it into 24 hours, etc., and you get down into seconds. It's now defined based on radiation from a cesium-133 atom. Very cool, but you don't need to remember that. In the SI system, for temperature, the unit is Kelvin. It's not degree Kelvin. I sometimes slip and say that. It's just Kelvin. I mentioned this earlier. Temperature is a measure of the average kinetic energy of the atoms or molecules that compose matter. So thinking about the solid state of students, if we were going to take the temperature of the room, we would take the average kinetic energy of all the people in the room. And like with many things, you don't all have the same energy. Some of you are real chill and some of you are a little bit antsy, right? So there's a variation. Temperature measures the average. Another thing that temperature affects is the direction of thermal energy transfer. Thermal energy can flow from one object to another, and it does so based on changes in temperature. So thermal energy will flow from a hot object to a cold object. So if you have a hot cup of coffee and you put a couple of ice cubes in it, thermal energy will flow from the hot coffee into the ice, melting the ice and warming that water up. In that process, the coffee cools down. It never happens that you put ice in the coffee and the coffee gets hotter and the ice gets colder. It doesn't work that way. Energy transfer is heat. We'll talk more about that later. There are two other units of temperature, Fahrenheit, degrees Fahrenheit, and degrees Celsius. And it is important for us to understand the relationship between these three units. So the Fahrenheit scale is what we use commonly in the United States. When the weatherman says it's going to be 105 degrees today, he means degrees Fahrenheit. Okay. In science, though, we typically use degrees Celsius. The definition, how these units came to be defined, is really kind of fascinating, but we don't have time to go into that. The Fahrenheit scale, just a very, very interesting history. And this is something that I never really thought of until, well, I can't say recently because I've been teaching this forever, but until I started teaching it. Where do units come from? Humans make them up, right? All units are just made up things. We have agreed that a foot means this. And back in the old days, a foot was like the length of the king's foot. And so the king dies and you got a new king, young king, and his foot grows. I mean, how does that work, right? So how do you define these things? But all units are made up. And some units like length, we don't have to define what zero is. Zero length is no length, right? But what is zero temperature? So on the Fahrenheit scale, zero is a different place than on the Celsius scale. That's a very weird thing about temperature scales. And then there's the Kelvin scale. So for Fahrenheit, zero was the freezing point of a saturated saltwater solution. There were reasons for that. On the Celsius scale, zero is the freezing point of pure water. And then on the Kelvin scale, zero is the lowest theoretical temperature, known as absolute zero. So what is zero on the Celsius scale is actually 32 degrees on the Fahrenheit scale. Water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. On the Kelvin scale, that ends up to be 273 Kelvin. Another kind of marker point is the boiling point of water. So on the Celsius scale, water boils at 100 degrees. So the Celsius scale is based on the freezing point and boiling point of pure water. The Kelvin scale also has 100 divisions between water freezing and boiling. And so a Kelvin and a degree Celsius are the same size unit, but the zero is in a different place. On the Fahrenheit scale, there's 180 degrees between water boiling and freezing. And so the conversion between Fahrenheit and Celsius is a lot messier. In Fahrenheit and Celsius, you can have negative temperatures. on the Kelvin scale, it's not possible to have negative temperatures. Because 0 is defined as the coldest temperature possible, you can't go below it. That makes it a useful temperature scale because there are calculations where if you end up with 0 and negatives, that can really just screw up the calculations. And so the Kelvin scale is useful for many things like that.
It said 0 degrees was the freezing point of saturated salt water for Fahrenheit. What's the difference then of like the 32?
So the 32 is the freezing point of pure water. So if you put salt into water, it will freeze at a lower temperature. Yeah. In fact, the last experiment we're going to do, we're going to make ice cream. And we're going to take some ice, and we're going to put salt on it. And we'll see that the temperature of that ice goes from about 0 degrees Celsius to like -8, -9 degrees Celsius. We didn't stick it in the freezer or anything. We're going to measure the temperature of it. You put salt on it, it makes it colder. When you think about it, that's really, really bizarre. But we'll learn why that happens. So to convert between these different temperature scales, we need to use mathematical formulas. And this is different than most other unit conversions that we'll be talking about. So these are the equations. I will give you those two equations on the exam, but you need to know how to use them. So if you have a Fahrenheit temperature and you want Celsius, you subtract 32, you take that quantity and divide by 1.8, and that'll give you your Celsius temperature. If you're going from Celsius to Fahrenheit, you're going to have to rearrange the equation. And we'll get some practice with that. I think I've got an example coming up, and then there's some problems on that worksheet. Kelvin and Celsius is just a matter of adding 273.15. So you take the Celsius temperature, you add 273.15, and that'll give you the equivalent Kelvin temperature. Okay, so here's an example. Gallium's a solid metal at room temperature, but will melt to a liquid in your hand. It's really, really cool stuff. Unfortunately, it's kind of toxic, so we can't just play with it. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on the Celsius scale and the Kelvin scale? So there's two things we have to do here. When we take degrees Fahrenheit and change it to Celsius, and then we also have to calculate the Kelvin temperature. So let's do the first thing first. So temperature conversions, we need an equation. And the equation relating Celsius and Fahrenheit is Fahrenheit minus 32 divided by 1.8 will give us the Celsius temperature. Here we're given a Fahrenheit temperature, and so we can just plug that in. If you don't have your calculator out, you should pull it out now. So there's understanding how to do the math, and then there's understanding how to communicate that to your calculator, and those can be two different things. Your calculator needs you to be very specific with it. So plugging this into your calculator, you can do it using parentheses. You need to put parentheses around the subtraction up here before you divide. Another way to do it is to take 85.6 minus 32, press the equal sign. That'll cause your calculator to finish that and then divide by 1.8. So my calculator is giving me I don't even know how many sevens are there, but there's a whole bunch of them. Right? Yeah, so we're going to learn about significant figures. For temperature, we can actually do it without sig figs. And it actually ends up being better. So the way you should round numbers for temperature conversions, look at the number that you're starting with. How many decimal places does it have? It has 1 decimal place. That temperature was recorded to the nearest 0.1 degree Fahrenheit. So I want to round my converted temperatures to the same decimal place. So I'm going to call this 29.8. 29.8, and the unit would be degrees Celsius. We need to convert our temperature into Kelvin also. We don't give you an equation relating Fahrenheit and Kelvin. You could find one, you could derive one, but you can also just convert Fahrenheit to Celsius and then convert Celsius to Kelvin. And so that's what we typically do. Kelvin is equal to the Celsius temperature plus 273.15. So I'll take my Celsius temperature and add 273.15. And I just left all the 7s in my calculator, so when I added this, I get 302.92, and it's got all those 7s. But again, I'm just going to round it to the same number of decimal places as the original temperature. 85.6 had 1 decimal place. I'm also going to round this one to 1 decimal place. And the unit is Kelvin, not degrees Kelvin, just capital K. Any questions? Oh yeah, they're the answers? Okay, nailed it. Okay, so in the metric system, instead of having what in the English system seems to be these really random units, like 12 inches in a foot, 3 feet in a yard, 5,280 feet in a mile. I mean, where do these numbers come from? They're just all kind of random. In the metric system, everything is based on factors of 10. So you have units that are 10 times larger, 100 times larger, 1,000 times larger. And so all we have to remember are those powers of 10, and those are related to the prefix multipliers. The multipliers change the size of the unit by powers of 10. So a kilometer or a kilometer, the prefix kilo means 1,000 or 10 to the third. So 1 kilometer is 1,000 meters or 10 to the third meters. So we've taken that unit of length, this guy right here, a meter, and we've made it 1,000 times bigger. We use the prefix kilo. The prefix kilo can be used with any unit. It can be used with meters, it could be used with seconds, it could be used with liters or grams or anything. It always means the same thing. And so that makes the metric system, once you get used to it, so much simpler, right? And this is the reason that I put on that list of material to memorize a bunch of the metric prefixes. You memorize the prefixes, and kilo means 10 to the 3. Now you can write a relationship between kilograms and grams, kiloliters and liters, anything involving kilo. So when we report a measurement, we're going to choose the prefix multiplier, which chooses the unit size that's going to be close to the size of the quantity we're going to measure. So if I had something that was 5 kilometers long, kilometer would be a good unit to use. I could express that in meters. It would be 5,000 meters. But we would prefer to use kilometers because it's close to the size of what we're measuring. So here's a table from the text showing a whole bunch of the metric prefixes. Now, all of these are not on the list of things to memorize. And I totally understand that there's these things that we should do that we would like to do, and then we can't do all of those. And so we kind of have to say, pick and choose and say, well, I can't do everything I know I should do, so I'm just going to do the most important things, right? That's kind of how life goes. So let's see, micro, milli, centi, and kilo. Those are probably the 4 most important ones. So if you can't get to memorizing all of the ones I told you to memorize, which is fewer than on this list, I don't care if you know what atto is, I can't remember that one. But get those. Next in importance would be, let's mark this somehow differently, nano and mega. Giga and tera you might recognize if you do anything with computers. Now the standard is, I've got a 2 terabyte hard drive. Well, they're using the metric prefix in front of a unit of memory, byte. So terabyte means 10 to the 12th bytes. So there's some questions on the worksheet that we're going to do that are more conceptual questions, and some students just really have a hard time with it. And so these 2 examples here are intended to help you with those questions. So how long is 4.5 capital M lowercase m megameters in meters? Well, instead of mega, the prefix, we can write what it means. So if you look in the table, mega means 10 to the 6th, or times 10 to the 6th. It multiplies the unit by 10 to the 6th. So 4.5 megameters is 4.5. Now I'm going to write what it means instead of the abbreviation. Times 10 to the 6th meters. This is what the capital M stands for. That's all the metric system is doing. Any questions about that? What if we had, let's just stick with 4.5. What if we had 4.5 nanoliters? Yeah, 4.5 times 10 to the minus 9 liters. Because if you look it up in the table, that's what nano stands for, 10 to the minus 9. So the metric prefix and the 10 to the something are interchangeable. It's like a name and a nickname. You can choose which one you use. The nickname, the prefix is shorter, and so that's what we usually use. We can also kind of do that process the other way. Oh, I didn't mean to use nano there, but here it is again. 7.13 times 10 to the minus 9 liters. Well, how many nanoliters would that be? Well, this means nano, right? So I can write in n instead of times 10 to the minus 9 liters. What if we had 3.1 micrograms? What does micro stand for? 10 to the negative 6. You can look that up for micro times 10 to the minus 6. So 3.1, instead of micro, I'm going to write what it means, times 10 to the minus 6 grams. Any questions? It is very, very important to understand the metric system. And a lot of students make it through Chem 3A and they're like, I got through there somehow, but I still don't really understand what they're doing with that. Today is the day to get it straight in your head, okay? If you're not really grasping the metric system, ask me questions in lab until it clicks. I'll stay here as long as it takes. So there are those base units, and then there are derived units. Derived units are derived from combinations of the base units. So length is a base quantity. The meter is the base unit in the metric system, kilometer in the SI system. Well, what about volume? There is no base unit. It's a derived unit. It's derived from units of length. So if we look at this picture here, that's me sitting in a cubic meter. So each side here is 1 meter in length. It's not a very good one. Try that again. 1 meter long, 1 meter wide, 1 meter deep. Well, volume from geometry is the length of it times the width times the height, right? So 1 meter times 1 meter times 1 meter, 1 meter cubed, 1 cubic meter. That is a unit of volume. It's derived from length. So as you can see, a cubic meter is a pretty big volume. You could sit comfortably in it, right? A cubic centimeter is just a little tiny thing, right? There's no way you could fit in that. So any unit of length cubed becomes a unit of volume. We use cubic meters, cubic millimeters, cubic centimeters, etc. We have some other common volume units, liter and milliliter. So these are typically used for liquids, just like in the kitchen, you might measure something in cups. You wouldn't measure it in cubic inches, right? Well, I'll have 7 cubic inches of milk. I want 1 cup of milk, thank you. So, how many small cubes measuring 1 centimeter on each side are needed to construct a large cube measuring 10 centimeters on each side? So here we have a little cube. It's 1 centimeter on each side, so that has a volume of 1 cubic centimeter, right? Length times width times height. And if the side here needs to be 10 centimeters long, that means we have to put 10 of those cubes together in a line, right? Along that one length. And then going up, we need, 10 layers, right? And then going back, we need 10 columns of this. So 10 centimeters times 10 centimeters times 10 centimeters, it's 1,000, right? So we've got the edge length is 10 centimeters, and this is a cube, meaning all the sides are the same length. And so that's 1,000 cubic centimeters. It would take 1,000 of those little blocks to make up the larger one. Mm-hmm.
So is a liter a derived unit, or is it not?
A liter is a derived unit. It just doesn't really look like one. Yeah. So 1 liter is 1,000 milliliters. A milliliter and a cubic centimeter are the same. 1,000 milliliters is the same as 1,000 cubic centimeters. And so I added this to the table. A cubic centimeter and a milliliter are exactly the same volume. They're just different names for the same thing. And in medicine, they, instead of calling it a cubic centimeter, they call it a cc, Give him 5 cc's of stat, right, on the TV shows. cc, cubic centimeter. Same thing as a milliliter. So this table gives a bunch of relationships between units, and we've got the categories here: length, mass, and volume. And we're going to be doing a lot of problems where we're going to convert units from one unit to another. There are green and yellow cardstock cards on the wall over there that are very, very popular with the students. I'd like to just hide them, but you'll find them anyway, so there's no point in me doing that. So you're welcome to grab one of these. Periodic table on one side. Very nice. And on this side, way too many conversion factors. Okay, just way too many. I challenge you not to look at that. Okay, don't look at that. You can do any conversion. I mean, you can just ask Siri or Google, right? And you can get your smartphone to do a conversion between, troy ounces and whatever. I mean, any weird combination. The point of all these problems that I'm going to have you do in the homework and on the worksheets is not to get the answer of what that unit relationship is. It's to learn the process of converting the units. And so the problems are set up so that some of them you have to put together more than one of these relationships. Some of those you can bypass by looking at stuff on the card, or you can look it up on Google. And yeah, you got the right answer, but you didn't learn the process. The process is going to be important when we do stoichiometry, when we're converting grams of hydrogen into grams of oxygen. That depends on the specific chemical reaction occurring, and you can't Google that. So we need to learn how to convert units. So I would challenge you to use this table. This pretty much has any relationship that you need. You might have to put a couple of them together, but they'll work really well for you. I put this should be available as a page on Canvas, or you can go to the PowerPoint slides and just take a screenshot and just have it on your phone and have it readily available. You could print it out, tape it inside your notebook, whatever, but I encourage you to just use this one. Another derived unit is density. Density is a ratio of mass to volume, and so we can describe that using an equation. Density is the mass divided by the volume, or D equals M over V. That's something you should memorize. It's the mass divided by the volume. So here's a fun question. Which weighs more, a pound of feathers or a pound of bricks? They weigh the same. Okay, which one takes up more space? The feathers, because their densities are different. Okay? If I take a piece of wood and I cut it in half, does the mass change? Yeah, the mass gets cut in half. Does the volume change? The volume also gets cut in half. So the density of the wood does not change. Density is an intrinsic property, and thus we can use it to identify things. Regardless of the size of the piece of metal, you can measure its density. Its density is the same. Whether you have that whole piece, you cut it in half, the density is still the same. And so knowing the density of different metals, you can identify what a metal is by measuring its density. So in your textbook, they give you this useful table, densities of some common substances. You do not need to memorize that, okay? But you might need to refer to it to do some of the homework problems. So those are listing densities in grams per cubic centimeter. Gram is a unit of mass, cubic centimeter is a unit of volume. For liquids and solids, for liquids we typically express it in grams per milliliter. A milliliter and a cubic centimeter are exactly the same thing. So here we have water is 1.00 grams per cubic centimeter. We could also say it's 1.00 grams per milliliter. because those are exactly the same thing. For gases, we typically use grams per liter because gases are so much less dense. And so we get a more reasonable number if we use a different unit. Density is a physical property that depends on temperature. When you heat something or cool it down, the density can change. It's not usually a significant change, but it does change. So density depends on temperature. That's why over here it's specified at 20 degrees Celsius. For ice and for water, they're listing it at 0 degrees and 4 degrees Celsius. So density is mass divided by volume. Does mass change with temperature? The quantity of matter? No. So if the density changes, it must be the volume, right? Volumes change with temperature. You've got a lid on a jar that's stuck. There's no strong person around to hand it to. What do? Run it under hot water, right? Why does that work? Because heating up the metal lid changes its density. It changes the volume of it. It changes the size of it a little bit, and often will give you just that nudge that you need to be able to open it. So this idea is going to come up on, I don't remember if it's a worksheet or a lab, but make a note of this. So density depends on temperature because volume changes with temperature. So we've talked about chemical and physical properties. We can also talk about intensive and extensive properties. The difference here is, does it depend on how much stuff you have? So if I'm measuring the length of a piece of wood, does it matter how big that piece of wood is? Yeah, because if it was a bigger piece of wood, the length would be longer, right? That's an extensive property. It depends on how much substance I have. The mass of something depends on how much of it you have. The volume depends on how much there is. Then there are intensive properties. They're like intrinsic properties. Density. The density of an object doesn't change if you double the amount or you cut the amount in half. It's always the same. The melting point of something doesn't change. Ice melts at 0 degrees Celsius, whether you have 1 gram of ice or 5,000 kilograms of ice. The melting point is the same. The color is the same. You take a piece of yellow paper and you tear it in half. Does the color change? Nope. The mass of it changed. The length of it changed, right? The shape of it changed, but the color didn't change. So those are intrinsic properties. Intrinsic properties can be used to identify things. So density is an intrinsic property. It can be used to identify things. So this, here I'm doing the example in addition to the 4 practice because they kind of build on each other. There's a story going on here. When I was growing up, we called problems like this story problems. Now I think they call them word problems, right? Doesn't story problem sound friendlier? Oh, it's a problem about a story, right? We get to hear a story. There's 2 kinds of people in the world. There's people who like story problems, and there's people who hate them. And you're usually in one group or the other. There's not really people who are like this, whatever. You get them or you don't. So if you're in that group of people that just, words, the word problems, just put it in a math equation. I could do that, but don't make me take those sentences with numbers in them and put them into a math equation. You can learn how to be better at that. It's not probably ever going to be your favorite thing, but you can learn to be better at it. So that's what we're going to do. We're going to learn to be better at solving story problems. So the first thing is you have to read the whole story. Now, a lot of times there's a bunch of it that is not critical to the problem, but it's there anyway, so we'll read the whole thing. Man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. He places the ring on a balance, finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? Okay, so some people can read that and just, oh, I know what to do. And a lot of people are like, I don't know. Well, we read the whole thing and then pull the numbers out. Pull the numbers out with their units, write them down somewhere. So here we have 3.15 grams. And we have 0.233 cubic centimeters. So it's asking, is the ring made of platinum? Next, you're going to look at the question. What am I trying to figure out? Is the ring made of platinum? How do I get that from these numbers? Well, the title up here might be a clue. Calculating density. How about we calculate the density of the ring? We could look up the density of platinum. If the densities are the same, then we can say, yeah, it's platinum. How do we calculate density? Mass over volume. So that's an equation. Density equals mass divided by volume. Well, do we know the mass? Yeah. It says he put it on a balance and he found it was 3.15 grams. Now, does it say the volume is anywhere? It gives the volume, but it doesn't specifically say, oh, this is the volume. It's talking about displacing water. So a ring is not like a cube where you can measure the length, the width, and the height, and then just very simply calculate. Especially if the ring has a curved surface, it's hard to do a calculation. So how do you find the volume? Well, you take a container of water, and you make a note of where the water level is. And then you put the ring in the water, and the water level is going to go up. Why does that happen? Because the ring takes up some of the space. It displaces, pushes the water out of the way. So when it says it displaced that much water, that is the volume of the ring. And that's a common scientific technique for measuring the volume of something. So that is the volume, it just wasn't specifically labeled. Okay, so we have the mass and the volume. We can put them into the density equation and calculate. 2, 3, 3. Always write the units. So I've got 3.15 divided by 0.233. And again, my calculator is giving me a mess. We're going to learn in a few minutes how to knock that down to a reasonable size. What happens to the units? Do grams and cubic centimeters cancel each other out? No. So what do? Oh, we just write them down. Grams per cubic centimeter. Okay? So, is that the density of platinum? No, it isn't. And this is where I'm not screwing this up too bad. So if we go back here, what's the density of platinum? 21.4. So that's why, you look at this ring, it feels kind of light, right? Like if you had a ring that was made out of aluminum, it would feel much lighter than a ring that's made out of gold. So is this ring platinum? No, it's not. So follow-up question. The woman in this example is shocked that the ring is fake and returns it. She buys a new ring that has a mass of 4.53 grams and a volume of 0.212 cubic centimeters. Is the new ring platinum? So we're going to calculate the density, right? Density is mass divided by volume. Here we've got mass of and volume of. So we can just put those in. Is this platinum? Yeah. When we looked it up in the table, the density was 21.4 grams per cubic centimeter. This is not exactly 21.4. But we're going to learn that all measurements have some uncertainty in them, and we're going to learn something called significant figures to help us understand how we should round this. Just a little preview, this number has 3 sig figs and this one has 3 sig figs, so this should be rounded to 3 significant figures, the 2, the 1, and the 3, and then this one is a 6, so I round up, and when I round this correctly, it does come out to be 21.4. Here's a conceptual question. We don't have to do a calculation here. The density of copper decreases as temperature increases. So you heat up metal. So the density of copper decreases as the temperature increases. That's because the volume changes. So when you cool something down, it shrinks, and when you warm something up, it gets larger. So if you increase the temperature, the volume gets bigger, and that causes the density to go down, right? So which change occurs in a sample of copper when it is warmed from room temperature to 95 degrees Celsius? Does the sample become lighter? Does its mass change? No. Does it become heavier? No. Does the sample expand or contract? It expands. So what's happening is that the volume is changing. Okay? We all should have learned density in elementary school. But some of us, it just didn't quite stick. But I find students in college, and you ask them, well, here's this little piece of wood and this big piece of wood. Which one's going to sink? And they're going to say the big one, because it's bigger, it's heavier. But its density is the same as the small one. The density is this weird thing you have to get your mind around.